In this video lecture, I will discuss basics of the laser. Laser stands for light amplification by stimulated emission of radiation. This is the full form of laser, because every time we use these words, energy levels or energy states, into the chapter of laser, so these two lines are just representation of the cells or orbitals in which electrons exist. This one is the lower energy level and this one is the upper energy level. So E2 minus E1, that is represented by delta E. This is one of the point and the first point of the laser basics. So the laser light is monochromatic, and that sometimes known as coherent light also. So what are the basic points related to if a source is coherent? Coherent light, as you know, that there is one frequency, single amplitude, constant amplitude, continuity and constant initial phase difference between these different waves emits from the source. The major point is that coherent beam of light is obtained due to stimulated emission of photons, which we discuss right now into the next slide, and these are the important processes which are responsible for the laser light. These are basically of three types. Three types of process take place into the laser action. Number one is known as absorption, and number two is spontaneous emission. Number three is stimulated emission. So these two are related with the emission of the electron. Emission are of two types, either through the spontaneously or by stimulated process. Here, first of all, the induced absorption or stimulated absorption is defined by using those two energy level correspond to the ground state and the excited state. Induced absorption is taking place when a particular frequency, suitable frequency of photon absorbed by the atom which is into the ground state. After absorbing this photon, this particular atom goes into the excited state. Here, after absorbing that photon of light, this atom goes into the excited state, that is defined here E1. Ground state is defined by E0. This is excited state. So in general, the difference between these two energy states, E1 minus E0, is equal to h nu. That is possible if the energy of the photon is comparable to the difference of these two energy levels. E1 minus E0, that is delta E, is equal to the h nu. Only then this atom can go into the excited state. You can understand that absorption is a process in which a suitable frequency of photon absorbed by the atom, and as a result atom goes into the excited state. There this atom stay up to the 10 raised power minus 8 second and less than that. This is known as the lifetime of the excited state, or simply this state E1. Lifetime is of the order of 10 raised minus 8 second, and then after this atom have to jump into the ground state, and that process is known as of emission process. So this was the case of absorption, and now there are two different processes. As I told you, one is of the spontaneous emission and second is of the stimulated emission, right? So in addition to this, I want to clear one more thing here, that this is an example of only one atom. This explanation of the absorption, whether you say it induced absorption or stimulated absorption, this explanation is only for one atom. When you explain the laser, then that time you consider an assembly of the atoms. There are large number of the atoms. Suppose there are n naught. N is a large number of atoms. Further, if n1 are the number of atoms into the ground state and n2 are the number of atoms into the excited state, the total number of the atoms is equal to n naught. So if suppose I have to find out the transition probability, that is denoted by P12, it means that atom absorb the energy in state 1 and going into the state 2. So this probability, transition probability, is defined by the two factors. One is the density of the radiation, that is defined by the u nu. U is small u letter, and here that is the function of nu, frequency. So this is the density of radiation. If you increase the density, obviously large number of atoms will absorb the energy and will go into the excited state. So second factor comes through the Einstein coefficients, and that is B12. Here B12 is the Einstein coefficient and u nu is the density of radiation. U nu is the density of radiation and B12 is the Einstein coefficient. These Einstein coefficient provide the information about the material in terms of the lifetime, decay width, right, of the energy level. The second case is of spontaneous emission. Spontaneous emission is the process in which basically the atom is into excited state, and after 10⁻⁻8 seconds, that is the lifetime of the excited state in general, this particular atom jumps into the ground state. So before emission, this is the process, and after emission of this photon, what is happening, this atom which was into the excited state is jumping into the ground state and emits a photon in random direction. So this is the difference between the spontaneous emission and stimulated emission. During the spontaneous emission, photons which emitted from the excited state, they emits in random direction, and hence they will not be in proper phase with each other. So this kind of light is known as incoherent light, and here you have seen that E1 minus E naught, that is the excited state and ground state difference, is equal to h nu. So h nu is the energy of the emitted photon, which is shown here, and the point is, in case of spontaneous emission, which you have to remember, number one, they are emitted in random directions, and number two, they are not in phase. So these are the two major points in case of spontaneous emission. But if suppose you have to find out the transition probability in case of when you are considering a large number of the atoms, then that is defined with the P21 prime. And again, the point of remember that this explanation is of spontaneous emission is explained by taking only one atom. So the transition probability you will define by taking a large number of the atoms, as we had discussed into the last slide, where n naught was the total number of atoms, n1 was the number of atoms into the ground state, and n2 were the number of atoms into the excited state. The total number of atoms n1 plus n2 is equal to n naught. So now the transition probability in case of spontaneous emission is defined only through the Einstein coefficient, and that we use a to 1. Actually there is no role of external source energy h nu, there is no role of it. So only the characteristics of the energy level play the role, and that comes through the a to 1, that is the Einstein coefficient in case of spontaneous emission. So here two things I told you, that the spontaneous emission process you can define by taking only one atom, and the transition probability you have to define by taking a large number of the atoms. And the spontaneous emission does not depends on the external source. It basically emits the photon through this process spontaneously. Here in case of stimulated emission, when you define it, that actually what happens, a one photon, this is the photon of external source, right? And here in this situation atom is into the excited state, that is in the excited state the lifetime may be of metastable state or maybe of the excited state, but the point is that atom is there in excited state, and when this photon, incident photon coming from the external source, looks this atom, right, here to this particular atom, what happens, this photon and this atom actually interact together, and as there is no any collision, that is basically the electromagnetic interaction, and because of that this excited atom get induced and jumps into the ground state, right? When the excited atom jumps into the ground state, it emits a photon of the frequency of suppose h nu 1. This h nu 1 you can calculate from the difference E1 minus E0 upon h, where E0 minus E0 is the energy difference between these energy level and h is the Planck constant. So this is the point about this photon which emit from the excited atom. And now what about this second photon which induce the excited atom? Actually this again passes without any interfere, and the frequency of that is h nu 2 for an example. So here in case of stimulated emission you are getting two photon of the same frequency and in the same phase. So this happen, actually nu 1 is equal to nu 2. This was just taken to explain that there are two photons, one is of the frequency nu 1 and one is second is of the frequency nu 2, but these frequency in case of stimulated emission are same, so we will use just only nu. How these two photons comes out in case of stimulated question? This may be a simple question which can arise here. So one photon is coming from the excited atom, and second photon which basically induce this excited atom is that one, right? And frequency is same of both the photons. So in case of stimulated emission we get two photons of the same frequency and in same phase. This is the property of the stimulated emission, same frequency, same phase of these two photons. So by this way one can say that we have amplified the light. So this is the process to explain the stimulated emission by taking only one atom, right? And now if you have to find out the transition probability P21 double prime, P21 we use for the emission process, but prime, single prime we use to spontaneous emission, and double prime we are taking for the stimulated emission. Right now this is the stimulated emission process, and we have to find out the transition probability that we can define only when we have large number of the atoms. An external energy source basically is playing the role. Use it in terms of the density of radiation. So we will increase the density of the radiation. Obviously large excited atoms will get induced and will emit the photons in this particular process that is known as stimulated emission process. So U nu plays the role, and the characteristics of the energy level comes out through the Einstein coefficient, that is B21. So now the total transition probability of emission is denoted by P21, and that is equal to P21 prime plus P21 double prime. Here P21 prime is you know that is only the Einstein coefficient A21 plus this U nu which we have written right now, and B21. So P21 is the transition probability for n number of atoms, and what was the P12 transition probability? That was U nu and B12. Here U nu 2 is the density of the incident radiation, and A and B are the Einstein coefficient. A21 we have used for the spontaneous emission, B12 we have used for the absorption, B12 we have used for the stimulated emission. So these are the three coefficients which provide the information about the characteristics of the energy level